So in lesson 23, you learn about the probability of based on an experiment, and consider the problem. A game at a school carnival has 3 different spinners. The spinners are shown. What spinner is more likely to land on A, section A? Well, first off, let's answer some questions. So how can you set up a ratio to represent section A on spinner 1? What fraction of spinner 1 is represented on section A? So what I would say is compare the part taken up by section A to the whole. It represents 1/3. So compare it to the whole. And then that would be 1/3. So then it says, is a pointer on spinner 1 more likely to land on section A than B or C? You can say no, because each section represents 1/3. So they're all equally likely. So the answer would be no. All right. Next one. What fraction of spinner 2 is represented by section A? Well, A is half of it. So it would represent 1/2. This would be 1/2. Okay. Next question. If I don't lose my pen here. Is a pointer in spinner 2 more likely to land on section A than B or C? Well, we would say, you would say yes, because spinner A is 1/2, while B is 1/4, and C is 1/4. So right here, you say yes, because A represents more of the section of the spinner. All right, next question. Whoops, never mind. Go back. It says, which section in spinner 3 is most likely to land on? To explain. So it will most likely land on C, because it has 2 sections. All right, last one. Explain how to use ratios to decide which spinner is more likely to land on section A. Well, let me just say this out loud, and I'll say it a couple of times, but I'm not going to write it down. So the fraction of a spinner covered by section A is a ratio. The spinner with the highest ratio is most likely to land on section A. So again, basically what it's saying is the fraction is a ratio for section A. So the spinner with the highest ratio, hence the highest probability, is most likely to land on section A. All right, this again is really not the main idea. We're going to do a couple more examples together. But first, let's find out more. So recall, experimental probabilities based on the results from an experiment and theoretical probability is what you expect to happen or the likelihood of an event. The sample space is set of all possible outcomes for an experiment. For all the spinners, the sample space is set of letters A, B, and C. The following ratio. So what we've been doing, we've been finding the theoretical probability of it. So for spinners 1 and 3, each section is equally likely. So these probability comparisons are uniform. Uniform means that they're the same. They're all equal. So the favorable outcome is the letter section of interest. The number of outcomes is the number of sections on each spinner. So for spinner 2, each section is not equally likely. They're non-uniform. The reason why they're non-uniform is because section A is bigger than sections B and C. So for the spinner, comparing this favorable section to the whole to find the probability. On spinner 2, section A represents 1/2. So the probability of A on spinner 2 is 1/2. And so on and so forth. So which spinner is more likely than others to land on section with letter B? So let me reread this. Which spinner is more likely than the others to land on section with the letter B on it? It would be spinner 1. The reason why it would be spinner 1, section B is larger on spinner 1 than all the other spinners. And so it's not comparing B to A and C on here, it's comparing B to all the other B's on these spinners. And so this one's 1/3, this one's 1/4, and this is 1/4. So you have a higher probability of getting B on spinner 1. All right, next problem. A family has 3 girls. The family tossed a coin to represent the likelihood of a girl if they have another child. The heads represent a girl and tails represent a boy. The table shows the results of their experiment. If the family has another child, predict whether the child will be a girl. All right, so let's answer some questions about that. Based on the results of the family experiment, predict whether the next child will be a girl or be a girl. Well, based upon their experiment, they have an 8 out of 20 chance for a girl and a 12 out of 20 chance for a boy. So they would say that I would predict a boy. So based on the results of the experiment, would the next child be a girl? And you say no, because based on their experiment, their probability was an 8 out of 20. And so what's the theoretical probability the next child will be a girl, which we just answered. So it'd be 8/20 or 2/5. Okay, let's see if... Nope. Okay, so the family tossed the coin 100 times. How would you expect the experimental probability to change? Well, I would expect... So the more times you do an experiment, you expect the experiment to get closer to the theoretical probability. So the more we do this experiment, the closer I get to the theory. And what I mean by theory is a theoretical. Will the experiment and theoretical probability of an event always be different? No, it will not always be different. There are some chances. No, each trial is different from the previous trial. So that means there's one chance that I do an experiment and the theoretical probability will be the same. It's not likely, but it doesn't mean it'll always be different. Okay, let's try it. Use what you've learned to solve this problem. What's the theoretical probability that the child will be a boy? Well, the theoretical probability of the child being a boy is 1/2. When you have a baby, you have a 1/2 chance of being a girl, 1/2 chance of being a boy. So in theory, I have a 1/2 chance of being, the baby has a 1/2 chance of being a boy. Does the fact that the family has 3 girls change the probability that the next child is a girl? No. So, and a lot of times people think if they have all girls, they'll continue having all girls. No. The fact is, the baby that you've had before does not change the baby that you will have. So you're going to say no.
Third run to the front. Third run to the front, please.
No, each baby will be different. Each baby is, let's say, is independent of each other. Okay, let's go on. So Serena is playing a game with the number cube. To win the game, she must roll the number 4 on her next roll. The table shows the number of times she has rolled each number so far. So what's the probability that Serena will win the game? Well, first off, we have to add up all the rolls. So if you add up all the rolls, you get 24. So for her to win the game, she has to get a 4, which she already got 5 out of 24 chance. So her probability of winning is a 5/24 chance. Okay? This is your experiment. Too many E's. Sorry, guys. This is your experimental probability. In theory, she should have a 1/6 chance because on a dice, there's only 6 numbers and one of them is a 4. So in theoretical probability, she has a 1/6 chance. But based upon her experiment, she has a 5/24 chance. Let's answer some questions. Oh, actually, let's do some try-its. So, explain how the experimental probability could change if you roll the number cube 200 times instead of only 24. So, if you rolled it more often, you have more data. So, first off, you will get more data. You get more data, and the closer you will get to the theory or the theoretical probability. When using experimental probability to make a prediction, what can you do to make your prediction more reliable? Well, again, have more data. The more times you predict it, the more times you do it, the better the prediction. So have more data or more trials or experiments. All right, let's go on.
Rebecca Burton to pick up, please.
Raphael tosses a paper cup, records how the paper cup lands. The table shows the results of the experiment. Predict whether the paper cup will land open and down on his next toss. Use a probability to explain a prediction. Well, his probability of open and down will be 4 out of 20, or 1/5. That's his probability based upon his experiment of an open and down cup. So why does it appear that the outcomes for the experiment are not equally likely? Well, the reason why they're not equally likely is because
Fourth run to the front, please.
why does it appear the outcomes for the experiment are not equally likely? Is because there are 3 possible outcomes, but it is easier. If I can spell easier. Again, I can't. It's the end of the day. Sorry, guys. 3 possible outcomes, but it's easier to get on the side. It's easier to get on the side of a cup than on the top or on the bottom because the side of a cup has more space. Okay. The paper cup experiment is non-uniform. Spinning a penny is an experiment that is uniform. Describe the difference and similarities between finding the probability of a paper cup versus finding the probability of spinning a penny. Well, again, paper cup is non-uniform, a penny is uniform. So you can assume the outcomes are equally likely for spinning a penny, but the outcomes for a paper cup are not equally. So you're going to say a penny is equally likely because you have an equal chance of getting heads or tails, while a cup is not equally likely because they're not all equal. Okay, how is predicting the paper cup result similar to spinning a penny? How is it different? Well, you can use probability to help you with your predictions, but you must use an experimental probability for the paper cup. So you can use probability to help with predictions on both of them. But the way that they're different is on the cup, you must use experimental because it's not uniform. All right, let's go on. And that's your homework. Okay, this one is really not more of finding the answers, it's more of comparing theoretical to experimental. So it's understanding what theoretical is saying, and it's understanding what the experimental is saying. So always remember that theoretical probability is in theory of what should happen. An experimental probability is based on what already happened. So remember, the more time you do an experiment, the more often, the closer that you should get to the theoretical probability. Other than that, have a great day, guys. Bye.